Okay, so welcome to the last day of class, I guess, right? You're not done yet, because there's not a pile of homeworks here, so I guess a lot of people are taking those late days or using them. That is good. And remember, the final product is so the homework's due whenever you turn it in, whenever you turn it in. But again, don't use more than your allotted late days. The project, the write-up, is due 12/12 by midnight. So just let me. Oh, is that something? Oh, that actually reminds me I should also do. 1 second. Okay. So the final project is due 12/12, which is Wednesday, right? Okay. Next Wednesday by midnight. I will mention also that at the end of class where to turn in. Boy, this is just really deciding it wants to show some fun stuff, doesn't it? Okay, go away. Man. There we go. Okay, so projects due then. I'll mention at the end of class because more people might come in by then, but if you're handing in your homework, I'm actually leaving for a conference this afternoon, so hand it in, just put it under my door and write down on the piece of paper when you turned it in. We'll be picking it up every day afterwards. I'll have someone come pick it up every day, so I guess you could, they probably won't be there on the weekends, so you could probably cheat a little on the weekend, but you know, as all things, I guess, has to go by the honor code, so please just write down when you turned it in. Let's see, was there anything else? We're going to not have, this lecture today is going to be just about some future directions of research. It'll be pretty short too, because I actually wanted to have a little questionnaire at the end of the class too. And then this is sort of in addition to the normal course evaluations. I'm curious about some thoughts on the course, etc. So it'll be all anonymous, but that'll be great if you can fill those out. So are there any questions from last time? If not, we'll just jump right in and we'll finish up the course. So remember last time we covered, in future directions, we covered a little bit on renewables integration, and we covered a little bit on security in terms of not the cybersecurity element, but in terms of stabilizing and reliability of these big systems, which is a very important issue. Okay, so today we're going to finish up on a couple future directions, and I'm going to be very brief on all of them. Today we're talking about a little bit about smart homes, and in particular I'm going to focus here on an area I work on a lot, which is the area of energy disaggregation. It's also called non-intrusive load monitoring, and I'll describe what that means in a second, and then give a very high-level overview about some of the work I've done in this area, to kind of give you a sense about what current machine learning types of research are on these problems. And I'll talk briefly about some work on demand response, and then even more briefly just highlighting some issues involved with things like microgrids. And that will sort of close out the things we're going to talk about today, and hopefully covers a very limited subset of the current pieces of work in sustainable energy, but at the same time showing you that there are a lot of areas where computation can play a big role here. So to start off with, these smart homes. I think the idea of a smart home has been around for a long time, right? The idea of somehow a home that would be more intelligent, both in terms of being better for the users that are inside there, and then also for using less energy. Typically, is a common motivation for smart homes. So they do things like turn off lights when people are not in the rooms, and predict when people are going to be home, and preheat the building, this kind of stuff. But I want to focus, and there's a whole body of literature on these topics, but I want to focus on a particular element which broadly goes under the category of smart homes, which is that of non-intrusive load monitoring. And this isn't really about a smart home in the sense that we're not really taking any actions in these smart homes. We're really just reporting information to the user, the homeowner, or whoever's living in the home, in a more intelligent way. And here's the basic idea. Let's see if I have, okay, I didn't just describe it from this slide too. So if you are a home owner and you want to know what's going on in your house, even I work in this area, yet I have very little idea about, until I started doing this at least, what was sort of really going on in my house. What was using this much energy? What were my big consumption spots? Where could I save energy? All this kind of stuff. And it's very hard to get that information from just like an energy bill at the end of the month, right? Because it just tells you sort of the total you use. Doesn't really tell you much about that. What we would like to have is a breakdown of the different types of appliances, or even of the actual appliances in the home, how much each of those are consuming, right? And in fact, a lot of studies have shown that if you just get this information, so you have some display that will show you how much power different sources are using, you will tend to use less energy, right? Because once you can see it, you can say, oh, I didn't realize that that heater was using so much energy, maybe I'll turn it down when I don't need it. This kind of stuff is very, very common. So giving feedback to users actually can be a really great way of saving energy, making homes more, in some sense, intelligent, without actually having to build in any real actuation into the home, right? All we do is we just build in the sensing. The problem, though, is to get the level of sensing we're talking about, right? Get device by device breakdowns of power. The typical strategy would be to put a monitor on every single outlet. So we need to take every single outlet in our home here, and either on top of it or behind it, put some sort of networked monitor that would all communicate. This is very expensive, and it's just not, in sort of the short term at least, it's not very realistic. Like, this is going to happen on a large scale, right? Because retrofitting every outlet in every existing home would be a huge undertaking, and this probably is not going to actually happen. So this leads to the idea of what's called this non-intrusive load monitoring method. And the idea here is that we want to achieve the same thing. We want to achieve device-level breakdowns of power, but we want to do it by only analyzing the whole home power consumption. Okay? And the idea there is that actually, for monitoring whole home, so monitoring all the power in your home, we already have the tools for that, right? Because all across the country, there are about 36 million smart meters that have been installed. These smart meters log information of the whole home's consumption, and at least on internal inside the unit itself, they're doing it about every second or so, or every couple seconds. And so the goal then, and I should mention this work has been going on for a very long time. There have been some very new, recent, exciting developments in it. But this is sort of the seminal paper that kind of summed up a lot of the initial work, was this paper by George Hart called Non-Intrusive Appliance Load Monitoring. So this was 20 years ago now. Yeah?
Are those device PMUs?
Now this is a home, so we're not talking about PMUs.
Home network.
This is a home. This is in a home. I'll show you an example in a second. So this is like in your home. So you probably, I don't have any PMUs in my home. PMUs are used to measure phase angles on the distribution, or on transmission network. So they're unusual to have as a personal, a personal device. Okay, so here's, maybe I'll make it clear when you have the picture here. So here is the power consumption in watts over about 40 minutes for my home one day. And this is the signal from a whole home energy monitor. And you can see that there's clearly stuff going on here, but until I actually looked at this, and if I didn't know what these already were, I'd have a sort of a hard time saying, well, what do I do in my house to actually consume less, maybe? And so here's what actually is going on in the home. So here, what we have going on is a washer dryer this is actually a dryer. I'm labeling it here by the circuit they're on, but this is a dryer that's running. We have some kitchen outlets that are coming on and off here. This is actually a coffee maker that I left on accidentally, so it's heating up the water and letting it cool back down. I'm not making coffee 20 times in that 20 minutes. And then I have a microwave that comes on at one point here, right? So we would like to give some display like this to the user, and sort of this, so they could see. And you can imagine, right? If you can see in your home what's happening on this level, you could realize that you left your coffee maker on and say, oh no, that was a mistake. I'm going to turn it off now. The problem, though, is that all we can get easily, of course, is this. And from this, it's not always obvious what's really happening. So what we want to do is use algorithmic techniques to separate out this signal into its different component parts, like this. And that's the problem of energy disaggregation or non-intrusive load monitoring. Now, mathematically, and I'll just sort of, I'm going to cover this at a very, very high level here, if anyone's curious, because it is using some fairly modern advanced machine learning, a little bit beyond what we covered in this course. But the basic idea is that we have some big vector here, right, of all the consumptions over the whole time. Each yi is just a real valued number. If you actually have a more complex monitor, you could, for example, monitor both the real and reactive power of the whole home at every time. Some meters can do that, but not that many. But you could have actually y's be vectors here, each one. But typically, this is just one big vector that makes up the total power of your home from some time at the beginning to some time at the end. And what we want to go to from this is a breakdown as a matrix, right, where each row here corresponds to the power consumption of a different device, of a single device, right? So we want to make a matrix like this such that the rows of this matrix sum up to the items in this vector here. Okay. And in general, these can be any other real valued number too. I guess they have to be positive probably, unless you have a solar panel, which might be negative power, but we'll assume these are all positive here. Now, unfortunately, this is a really hard problem. As you can imagine, there are a lot of different possible ways, in fact, an infinite number, of course, that you could make a matrix that sums up to the same vector here. And in general, this problem is actually, unlike some other machine learning problems we've talked about, we actually have more outputs than we have inputs, right? You have a higher dimensional output than you have an input, and so this can be a very hard problem to deal with. Now, the trick that we apply here is, well, there's a few tricks, but one of the big tricks is that when you look at this sequence here, what you'll notice is that devices typically consume power at different discrete levels, right? So when this device is on, it's consuming one level, one is off, it's consuming another one, right? So there isn't like, I mean, some devices like maybe a dimmer light could smoothly interpolate between different power levels, but most devices don't. Most devices have different discrete levels of power. And so we're going to exploit that actually to, rather than, and I'm just going to change notation a little bit here, rather than talking about y's, I'll talk about x's, because the x's here are going to be some number of discrete values. They can only belong to some reduced subset, which corresponds to the power consumption in different states of these appliances. And I apologize again for one more set of notations here. This is actually my own work. So I could probably try to be a little more consistent here, but this is the notation we use for this type of paper, so I'll just leave it as this. Now, unfortunately, this is still a really hard problem, right? It's still actually very hard to say, okay, even though we now might be more well-defined, we can say, which combination of states here add up to the total amount. The only way you can actually solve this is to check all possible combinations of different states a different device could be in, and that complexity grows exponentially with the number of appliances you have. And the numbers, and I guess it's k to the n, where k is the number of states per appliance and n is the number of appliances you have. So, and in fact, actually, I should mention even more than this. The other thing we can exploit is the fact that there is this kind of temporal regularity here, right? So if a device is on, it's more likely to stay on, and if it's off, it's probably going to stay off. You don't have devices that are every second switching on and off randomly. That would be a pretty unusual type of device, right? They typically go on for a while, then go off for a while. And one way of modeling this is with what's called a factorial hidden Markov model. Now, we didn't talk about even really hidden Markov models at all. Hidden Markov models are like an MDP, where you don't observe the actual state, but you also can't take any actions. You just have some sequence that evolves over time, probabilistically, and you observe some function of it. Now, a factorial hidden Markov model is like that. And essentially, what's really happening here is that at every time point you have some state x, that's some energy level, and what you observe is the sum of all those energy levels. And Though we didn't cover it, this is a figure known as a graphical model representation. And if you take more machine learning courses, you'll run into graphical models a lot. And this is just a graphical way of representing the dependencies between these different elements here. So all this is saying is that the state at time t is probably going to be influenced by the state at time t plus 1. And it will influence the next state as well, right? Because states tend to stay on for a period of time and turn off for a period of time. What these arrows here mean is that what we observe, which are the gray nodes here, is going to be the sum of these different unknown values here. And we want to find from these things, we want to find the values of the different nodes. So again, don't worry about the details here. Just the overall idea is that this is just a little bit more rich representation than what you had in the previous thing, because it also captures dependencies between different time steps. Now the challenge, and this is the only slide I have on this, so I'm not going to cover it all in any detail, but a big challenge with these kind of models is that this task I was talking about before, which is called the inference task. The inference task is, from these observations, determine what the different power levels the different devices are. This, as I said before, this is a very hard problem, right? All you can do, and this holds the same for these probabilistic models, all you can really do is check every possible combination of appliances and go through that exponentially growing set of possible combinations. And it's not very efficient. Now, what we do instead, and in fact, for a real home, there's far more appliances even in a real home than you could really do with a model like this. That one I showed you before was pretty simple. There's only a couple, but there's actually a lot more in that house that could be on then. So what my work in this area was essentially using new methods for solving this inference problem. Okay, so how do we learn what these values are given, it's not learn, how do we compute what these values are given these outputs here? And the way we do that is, as is everything else in this class, is through optimization. So it turns out that this hard counting problem, you can actually perform what's called a relaxation on it. So if you form that as an optimization problem, it will be non-convex, right? Because there are these constraints where things have to be in one state or the other. And what you can do instead is essentially relax these problems such that you can be in some combination of states. Now, typically that's a bad thing, because you don't want to say that some refrigerator is half, or some power source is half of a refrigerator and half of a dryer. That wouldn't be very likely. But if you play some clever tricks, what you can do is actually transform this to a case where you relax the problem, and then add some additional constraints that, even though they are convex, discourage situations like that. And so, I mean, very, very hand-wavy here, but the idea is by playing some tricks in the optimization problem, you can actually come up with ways of solving this problem, which definitely aren't guaranteed to work, because in the general case, this is actually an NP-hard problem. But they often work very well for cases that we actually see in practice. Yeah?
What do you mean by relax the problem?
Yeah, so we didn't really talk about, that's actually a technical term. We didn't really talk too much about integer programming in this class, or binary programming. But essentially, you could have some optimization problem where you want to minimize over x of some function of x, right? Subject to a constraint that maybe x is, say, a vector in Rn. Subject to, and I guess this is sort of bad to write here because I'm going to constrain it much more now, but also the fact that each xi is actually going to be in 0 or 1. Okay? And this is what's known as a binary integer programming problem, because you're constraining your x's here to be binary valued. Now, this is a hard problem to solve in general. There are some sort of nice solutions, and actually Cplex has some very fast, approximate ways of solving things like this. But in general, the only way to solve these things is to, because these constraints here are non-convex, you can't write this sort of as in the form of any convex function. Because of that, all you can do is basically try out every single possible combination, right? Try out every single combination, in which of course there's going to be two to the n different combinations of possible values. The relaxation of this would be say, well, what's the closest convex problem we can come up with that's close to this? And what that says is that we're going to replace these constraints that they be either 0 or 1 with the constraint that they be between 0 or 1. And this is sort of this is now a convex constraint, right? This is just a linear set of constraints here. And what it captures is the fact that we're going to allow for these things to take values, kind of intermediate values, which isn't really allowable, right? Because if this is things like, well, is a device on or off, you can't have a device be half on. It's just not physically possible in a lot of cases. So these things, in the worst case, work horribly, right, as you would expect, because these problems are very hard to solve. But you can play a lot of tricks in a lot of cases where you do this, you add some other constraints, maybe you know some other things about x that might encourage it to take on 0 or 1 values, even if it doesn't have to. And you can do things like this that actually oftentimes work quite well. And will oftentimes, when you actually solve them, so maybe you add some other constraints that x is in some set C or something like that. What happens though is when you solve this problem without these constraints, but with these relaxed constraints, and these are called the relaxation of that, you end up typically getting integer solutions anyway. And if you get integer solutions, because this is sort of a more general problem, and so a more like a looser set of constraints, if you get integer solutions with this problem here, you actually know that you've solved the original hard problem, right? Because this any sort of function here will always be less than that. So if you get integer constraints, you know those have to be the optimal ones. For this more general problems, they have to be optimal ones for that original problem. That's sort of very hand-wavy here, because of course the hard part is what constraints do you add here, how much do you add, how do you do this kind of stuff. When is it guaranteed to give you a solution and when is it not? These are all very, very complex issues. But it's sort of a common technique and a lot of problems that can work very well in practice. Yeah?
So is there any electric appliance that works like the curve is like something smooth?
Not in this house. And it actually happens a lot less than you think. There are these types of appliances. One thing that happens for a lot of appliances is the way that they actually work. So this dryer, for example, here. I'm not, again, turning my dryer on and off every minute. What's happening here is that in order to maintain temperature, the dryer will turn on, turning heating element completely on, and wait for the temperature to go up to a certain point. Then when it reaches that point, it goes off until it hits another point down there, right? So the temperature is called a duty cycle behavior, right? Where the temperature essentially will go up to the top band point, then go down to another lower one, and go like this, right? And the way you do that is you turn on the dryer, the heating element there, and turn it on here, and just turn it off there. So even devices like that we think might be smooth. You could have a continuous type dryer that, just turns it on to some level in the middle to maintain power here. But it's very common to just see this kind of duty cycle behavior. In fact, a lot of devices that look smooth are just doing this at a much higher frequency. So if they do it too frequent, we can't see it in the power, so it looks just like a smoothed out thing to us. But this is the idea of switching that we talked about in power electronics, right? A lot of times you do this anyway, and you just smooth it out a little bit to make these things look a little bit nicer.
So here you're just measuring the power curve, right?
Yeah.
So is there a possibility that we can use specific signal?
Yeah. So certainly you can use actually the whole current waveform to look at, you could look at like real and reactive power, for example. You could also look at the actual current waveform, because a lot of devices like those power electronics put very interesting signatures into the very interesting electrical signatures.
Is there a way that we can, let's say, we can create information flow, add some signal in the power.
Oh, you mean actually have the devices communicate their power consumption? So if you're going to do that, then you're talking about actually changing the devices. It's probably easier to just network them and have them send it to some router, right? Then, I mean, you could send it over the power line too. But that's sort of the same mindset as monitoring outlets, right? That's basically building new hardware in the appliance itself that communicates its power consumption. And I think that's certainly a way we can go in the future. But right now, the idea of sort of retrofitting every appliance that's already there with some communication technology and monitoring technology would be pretty hard to do. So this is sort of the cost-effective alternative to that, where you don't have to go through all that effort. Yeah?
So I guess in the earlier machine learning lectures, you did one on classification.
Uh-huh.
And then you did a similar...
Right, yeah.
So what's the difference?
So the difference is that the goal of classification is to sort of, and they're very similar. The classification approach essentially just says, I want to determine if a device came on right now, if some event occurred. Whereas this is looking more kind of over a longer period of time and saying over this longer period of time, what's happening in general. Now, you can go from the classification, if you can classify everything kind of correctly, when things turn off and when things turn on. If you classify everything correctly, then you just kind of take a running sum over time, right? You just sort of say, okay, this is what's happening. I know I have my signal here. It looks like this. I know that the dryer came on here. I know the dryer turned off here for my classification task. I'll just sort of add up this power as it goes over time and add it to the dryer amount. But that sort of takes an extra little step, right? Because you have to actually post-process your classification results to get an actual breakdown of energy. So this is just kind of a different way of looking at it. And actually these two ideas, these event-based approaches, so actually that idea was exactly how that first paper worked, that paper by George Hart worked. These are sort of two current approaches to how you address this problem. And there's a lot of ongoing research in both those two kind of paradigms. Do you detect events, or do you kind of just separate out sources? And there's a lot of course, similarities there, but there are also some significant differences in what you want to go about doing, depending on what your goal is.
So if you detect events, how do you distinguish between the appliances?
Well, that's the classification problem, right? That's what you classify. You say this event is washer dryer. That's what we, and not, or this fridge and not that fridge. That's the classification task. Okay, just to show you some kind of results we get here. This is sort of existing methods for solving this problem, which work pretty poorly, and then we have some newer methods that work based on these relaxations here that work very, very well. So, and just to sort of give some numbers out, in one framework for not just this sequence here, but for 2 weeks of data in a home, older approaches got something like 35% of the accuracy they were assigning correctly, which is not horrible. There are 10 categories of devices here. So they can, that's assigning it, getting it right out of 10 different ways. But we're doing, of course, much better here in terms of we're getting 87% accuracy in what we assign. So, and I should mention, this is all described in this paper, which you can link to which is linked through this PDF. This is the only paper of mine that I'm putting here. I'll, try to hold off on putting too much of my own work in in the class, but this is sort of our approach to how you solve problems like this, and with these convex relaxations. It'll be somewhat technical, this paper, so I don't worry if you don't quite understand it even after going through the machine learning units here. But if you want to sort of follow this line of work, you can do things like take courses on graphical models here, which I think one's being offered next semester, and courses on machine learning, and then you'd be able to understand exactly sort of what all our models and relaxations are that we're using here. So I want to kind of go a little quickly here. I think I want to try to end a little bit early. But the other two things I wanted to mention as go through these fast, but just to mention as areas of current and ongoing research are, first of all, demand response, and then secondly, microgrids. The idea of demand response, which you've probably heard that term, or a lot of you have heard that term before, is that in this course, and in most treatments of sort of power economics, right, at least most past ones, load, the amount of power actually consumed by customers, was treated as a fixed quantity, right? You just saw whatever load was what people were using, and you had to supply that. And that works okay, But as we sort of start to consume more electricity, especially with things like electric cars that just consume a huge amount of electricity, and just as the consumption increases in general, and we aren't building that many more transmission lines maybe, so we need to be more efficient, and we want to be more efficient in general, we might want to think about adjusting load in the same way we adjust generation. Right? And with communication, we can do that. We can sort of say, hey, we have to think about the right ways of doing this, because there's all sorts of, you wouldn't want to just start turning things off, certainly, but you might want to have some framework set up where a person can say, okay, on a really hot day, I'm not going to run my air conditioner quite as, or really, I guess a hot day, maybe I'll, won't run my air conditioner quite as cool. That'll save some electricity, because usually those days are very bad for using a lot of power. So I'll let my air conditioner, run a little bit less aggressively, and maybe I get some incentive for that, right? Maybe I get a little bit of money back on my electricity bill, in addition to what I would save anyway. All right, so this question of how do we adjust for the possibility of, giving people incentives to use less electricity, and how do we do that in kind of a market framework in real time, has spurred this whole area of demand response. And there's a ton of work in this area, and by all means are these the main papers, or the only papers. But for example, in the 2000s, and this has been studied for a long time too, so in 2000 there was this paper on how do electrical markets change when you allow factoring in of elastic demand. So how can you send signals to people that would make them change their consumption? Again, we sort of were under the paradigm where pricing wouldn't affect consumption, but that's only true to a certain extent, right? If you change price a lot and you give people the option to adjust to these prices, you will probably change consumption. There's a lot of work on automated ways of doing this. I think there are actually a lot of pilot programs out there right now where homeowners can opt into a system where the utility has control over their thermostat, and on certain days of the year they will turn their thermostat up if they need this to meaning not as cool, because these are usually on the air conditioning days. So that there are ongoing ways of basically giving some control to the utility so that they can actually, in their big optimization problem, you can actually adjust those load values a little bit rather than just having them be fixed. Right? I want to talk about one example of that, which is some some work that's done by Duncan Callaway and his group. He's a professor at Berkeley. And the idea here, and actually one student in this course was doing this for his final project. So I actually got acquainted by this work through the final project in this class. But I think it's actually a great example of showing that the stuff we've learned in this class really, it's not just that I'm saying it's useful for everything. It's that these things are really being used very, very widely in a lot of papers like this. So the idea here is that we want to be able to control loads, thermostatic loads, and these are things like refrigerators or air conditioners. And the point is that what I showed here before was that these devices operate essentially to maintain temperature within a certain gap, right? So the only goal of an air conditioner is, say, to maintain your house between 70 and 73 degrees, say. And within that temperature bandwidth, you just say, maybe you turn your set point to 72, but you can say, okay, I can be a little bit misty in either direction, and it's fine. In fact, they do that already. If they didn't do that, they'd have to turn on and off constantly to kind of keep that exact temperature. So they have a little bit of a gap where they say, okay, it's okay to be within this gap here. Right? And the idea is, as long as you're maintaining things in this gap, you can really do whatever you want with these loads, right? You could turn them on here, like this, which is kind of the standard way of doing it. You just wait till it gets to the hottest point, or whatever. I guess this is a heater, so you wait till it gets cool, you turn it on, and wait till it gets to the hottest point, then turn it off, and you just go like that. But you don't have to do that, right? You could control them differently. Turn it off maybe when it gets here, right? Can everyone see this is sort of a very small drawing I'm making? Maybe I'll make a little bit bigger one. All right, so you have some upper bound, and you have some lower bound on temperature. And commonly, devices will just turn on a heater, for example, will turn on until it's, an air conditioner will do it in reverse. It'll turn on until it's as hot as you want, or as the upper limit, then turn off, and it'll sort of, at a different rate, it'll come back off. And you'll turn it back on, and sort of just go back and forth like this. And so it's on in this range here, off here, and then on here. But there's no requirement to turn it off and on like this, right? We could have turned it off here. That's fine. We're still within that bandwidth. And the idea is, can we intelligently control these devices? If we have one, we could do maybe a little bit. But if we have a lot of them, well, maybe we can coordinate these somehow to actually, as a total, turn on and off at the right times to actually provide some sort of tracking, be able to track small changes in load, say, of wind power or something like this, right? So can we adjust these things in a way that actually achieves desired behavior for their total consumption? Now, we can't actually completely eliminate their consumption, of course. All we can do is shift it in time a little bit. We can say, okay, we're going to consume here instead of here, maybe. But when something like wind is blowing, right, and you have the variability in wind, the ability to sort of change your demand even over small time periods is very, very valuable. And so that's what these kind of papers look at. And they look at it actually doing it in a particular way. They look at it in the situation where you only have one control action you can send to all your refrigerators. You can't sort of control each one individually, because that could be a lot of sort of computation, right? If you sort of needed to sort of compute, have a state space with say, 10,000 different states of the refrigerators, that would be hard to solve, even with something like MPC, right? So instead what they do is they actually say, I'm going to send out a single control signal to all the refrigerators. And what that control signal will say is what action you should take, basically turn on or turn off, given that you're in different ranges of temperature. And they're going to broadcast that to all their refrigerators. And they're only going to measure the total consumption that all of them together are consuming and see how well they can track, desired patterns and energy over this whole aggregate amount of refrigerators. So the state of their system, something that looks like this. And again, this is just a figure from the paper. Don't worry about it. It's a little bit confusing. You can look at the paper. Actually, the paper should be quite readable, given all that we've learned in the class so far. They use a Kalman filter here, which we didn't really cover, but you sort of know a little bit about what that is, so it should be hopefully pretty readable, this paper. But the idea is you take this temperature bandwidth here, and you chop it up into n different bins. Okay, so each of these bins here represents one sort of little range of temperature. So that's the x-axis, represents different sort of temperatures for each appliance. And then this thing here represents, are they on or are they off? So typically what happens is that the temperature, it turns on, some turns on, you increase temperature. Actually, is this right? I guess this is showing, this might be showing an air conditioner, right? So it's showing the arrows this way. So you turn it on, that will, no, it's showing a heater. You turn it on, take it back, air conditioner. You turn it on, that will, if you turn it off, that will let temperature increase. Then at a certain point, temperature's gotten high enough, so you turn it on, and then it cools it back down. I guess this is a refrigerator or an air conditioner or something like that. And typically, you just follow this sort of pattern on the outside here, right? You sort of go through the states like this. You let the states cool down, heat up for a while. You turn the air conditioner on, and then you let it cool back down. You turn it off, and it heats back up, and like that, right? But of course, you could also tell it, if we're in this state, we'll go to there instead. Turn off if you're here instead. And what they do is they just basically send out signals that says, for each of these bins, turn on or off depending on what your temperature is. So you still have to have that ability in the refrigerators themselves. They still have to be in sometimes smart refrigerators. But they don't have to have sort of individual communication telling, with you. So they're telling you exactly what their power consumption is and what their state is, etc. All you say is you measure the whole sum of all of these things, and then you send out a broadcast signal that says, turn on if you're in this state and turn off if you're in this state, etc. So I'm not going to go through the details of what they do, but just these are some of the equations they show in the paper. And hopefully these are actually quite familiar to you now that you've gone through this. So just I'm highlighting the fact that these are very, very common models here. So these are the equations from this paper. What they have is they set this up as a linear dynamical system. It is a partially observable one. So we don't observe the state of each of the refrigerators. What we observe instead is their total aggregate output, right? We observe sort of the sum of the powers of all the ones that are on. In the control task, our cost function here is the sum over all times in a horizon ahead. So what the notation here is saying, we're going to start at our current time k and go to some horizon n pred. That was the h horizon for MPC. They are using MPC here. So we're going to sum from our current time to some time in the future. Some error that penalizes how well we're tracking our desired total amount of power. Some error that penalizes essentially control actions for the bins. You don't want to spend too much control. You basically want to let it do what it wants to do normally as much as possible. And then you also want to maintain each one in its set point. So these are the three elements of the cost here. And it's just a quadratic cost, exactly like we saw in the class. Finally, you also have constraints. So the actions here, what the state corresponds to is actually the fraction of devices that are in each different state of this kind here. That's the state. So the x vector is, I guess, n bin. I guess it's just an n bin dimensional state vector by the notation here. And you can read the paper for details, but essentially these matrices, by putting it in a certain form and making u be essentially the number of devices you switch from one bin being off to one bin being on, which are the actions that you have, you can make this a linear dynamical system. You have linear constraints here. You have a quadratic cost function. And so you solve it with, in our case, MPC, or in their case, MPC. Okay, so these are things that are actively being done in a lot of papers out there. This is, in fact, almost exactly what you guys did in the last homework, or maybe are still doing. And this is the kind of results they get. So this loads. I know these ones were big images. Wait for it. OK. So what happens here is that this graph here shows the temperature state. I guess these are definitely going to be, yeah, OK, right. So this is some air conditioner here. So this shows the temperature state of all the different devices. And they have 200 of or they have 1,000 total, and they're showing 200 here. So what you see is together they all can be in different states, right? As you would expect, there's some randomness involved. One might be the top state, one might be the bottom state. But they're all staying within this desired region here. And by controlling them intelligently, you can actually follow, and you can't even really see this, but essentially their desired thing they're trying to track in aggregate power is a pretty big change in total consumption here. It's going from 3 megawatts to maybe 12 megawatts of power over all of them. And you're tracking kind of very detailed curves in power. This sort of desired trajectory, for example, could be the response to some, say, wind conditions, right? So it could be kind of caused, I mean, it wouldn't look quite like this. They're just showing some examples here. But maybe this little noisy part here is caused by some wind that's coming on, going out of your system. And you're going to use these loads to track those deviations. So you don't have to worry about sort of spinning up expensive generation. You can just track it here with refrigerators that already exist. And you'll see, like, for example, where you want to track a really low set point, that means they should all use power. Sorry, that means they should all give not use power. And so the temperature in all of them goes up very high, right? So you basically, when you're trying to use less power, everything goes up very high. And when you're trying to use a lot of power, this falls back down low. Now, you can't, of course, track any signal here, right? Because at a certain point, they would all get to the top state, and you have to just turn them on. You can't avoid that fact. But for short things like this, where there's some randomness and there is sort of a zero mean, this has to be zero mean, I should add too, right? Because otherwise, they're going to use the amount of power they're going to use anyway. But by doing this intelligently, you can track very complex power outputs like this. And again, if you want to listen to more details, this is from the Koch et al. Paper, but it's the same group doing both these papers here. And you can look at the, I guess, Koch or Koch, I don't know how that's, which one's the pronunciation there, but these are both links here, so you can check them out if you want to see more. Okay, so finally the last thing I want to talk about, I only have, I think, 2 slides on this, is microgrids. And the idea of microgrids is, we've been talking in a lot of this class about either kind of the home level, right, with like device identification, or I was talking about this time before, sort of disaggregating different consumption in a home, or we've been talking about kind of grid level stuff, right, where we're talking about the entire power grid of big generators and big consumers. And microgrids kind of lie in the middle between these two things. The idea is that we're going to have something like a real grid. So we're going to have some generation, maybe some storage. We're going to have loads there. But we're going to do it at a much smaller scale. And the advantages here are, there can be a lot. You can have much more efficient consumption because you're not maybe transmitting your power over long distances. You have a solar panel right there by your home. You can use that energy very efficiently after it's been generated, I should add. It also can be more reliable, right? Because even if there is a big outage to the actual grid, presumably if the grid does not go out, you're still typically hooked up to the grid in a microgrid. So you can always use the grid if you want to. But in the case of some outage, you still have all kind of the local supply that you need, right? You have generation locally, you have storage locally, you have all these things that can actually sort of help you. So they can actually be more reliable. And there's been a bunch of papers on these things. I don't think any of these are necessarily the one paper to look at, but there's been a lot of papers on just describing the overall idea of microgrids. These are sort of very general survey papers describing this idea. So for example, here is one figure from this paper of a potential microgrid. Now I won't go through, actually it's kind of hard to read on this slide here. I hope it's a little easier on the PDF itself. But essentially, you have some connection to the grid as a whole. You have some transformer there, because you probably want to have a lower power than high voltage lines for your microgrid. And you also have these little squares here, which are circuit breakers, which essentially can isolate you, if you want, from the rest of the grid. So you could run entirely locally. And on each end here, each thing behind every circuit breaker, what you have here is you have some little hourglass thing, which is meant to be either a generator or a consumer. So it can, things like storage or generation, for example, would be one of these things where you can either consume energy, power to store something, or you can put back power on the grid, or you can just do it from, say, a solar panel. You could just be generating energy. So I guess arrows down are always loads, and sometimes arrows up could be generation, I guess. So they're using this little symbol as the load or generator. And what you'll see is that in order to exist behind a breaker box here, you have to have one of these loads or generators, right? Because if you didn't have one of these and you ever turn this off, you would just shut off every one, right? So the one station here that has no generation, that just is hooked up to the grid as usual. But then there are all switches here, and they can be hierarchical, right? So you can have one that isolates all of these, and then each one can isolate itself, etc. And again, I'm not covering this in any detail here. I'm just sort of getting the broad idea here is that you create all the elements of a typical grid, you just do it at a much smaller scale. And you do it in a way such that these ideally can be self-sufficient if they want to be, or maybe self-sufficient for a certain period of time if they want to be, while you can also just, in the worst case, draw from the grid as you would normally. And again, what people mean by microgrid sometimes changes. So you might hear that term apply to a lot of things, but this is sort of the typical context of it. And I think a lot of the ideas that we covered in this class, right, of planning and storage and control, all these kind of things, they will come up the exact same way in microgrids. And they'll do it at a much smaller scale, so you actually need more computation locally in order to coordinate the resources behind this area if you do lose connection to the actual grid, or if you do disconnect intentionally from the actual grid. You need that kind of local control, that local planning. You need to understand the power. I guess power flow, depending on the size of it, might be an issue or it might not be, but it could be an issue even for small systems. So you need to understand all those things in order to run this microgrid. And you have to do it, all these things we've been talking about, you have to do it at that small scale.
Would it be easier because it's at a small scale?
It certainly, yeah, probably would be easier. I mean, the ideas are it can probably be a little bit less intensive than the massive optimal power flow you run for the grid. It can probably do things like demand response also, because you could just, sort of the ultimate demand response, right? You could just isolate it entirely from the grid and give that service to the grid. You can do things like store power stuff locally and then just use it when you need it. You could store power from the grid while everything's going well, and then only go off if the grid goes down or something like that. So all these things can need to be dealt with, but yes, because they're smaller, they can be dealt with better. But at the same time, if everyone was doing this, you'd have a lot of different control going on, and in total, that would actually be quite a bit more, right? Because these are much more flexible. There's more things you can do here. So it's sort of a, there are pluses and minuses from the complexity side, but I think overall the potential gains in efficiency and reliability are very appealing here. Okay, so that actually brings us to the end of the course. So just some final thoughts here, and I'm also going to end early today. But big picture, right? Let's just sum up everything we learned in this course. I think probably a lot of you are here because you saw the course title, right? And you personally already were interested in sustainable energy. So at least that bit will probably be easy to convince you of, that sustainable energy really is one of the grand challenges that the world is currently facing. Right? And I also think that it's equally clear that there's no easy solution to this, right? Maybe if we invent, fusion, cold fusion, that's about as easy as you can get, but calling that easy is sort of funny to call that easy, right? And even then, it wouldn't be that easy, right? Because there'd be all sorts of regulations about how you, anyway. So I think it's obvious that this is not an area where there is one solution to the problem, and it's not an area where there's one field that is tasked with solving this entire problem, right? It's not like this is going to be solved by electrical engineers doing work in the smart grid. It's not going to be solved by materials people building batteries or by computational people running algorithms, right? The solution to these problems involves combinations of all these elements. You need the materials, you need mechanical engineering, you need civil engineering, you need all these things to come together in a way that addresses this problem from a big perspective. And computation is one piece of that. It's not the solution. There's no problem, no optimization problem you can write down where if only you could solve that, then we would solve the world's energy problem, right? But computation can play a key role in transforming a huge range of these areas, right? It can transform work in the smart grid because we have the ability to do this online planning and online optimization. It can also affect things like design of maybe materials, right? If they can use more computational techniques in designing those things, and this is sort of far afield, certainly, maybe we can advance that. Now, these are not things that have been necessarily done to a great extent already. These are sort of future topics to work on. And I think that really the most exciting stuff is yet to come. So hopefully all of you can be excited by these issues. I think you all are. And I think you're come from a wide range of different backgrounds. So the hope is that you'll take these tools and you won't treat them as the solution to the problem, but you'll treat them as a very, very important tool for you to use in thinking about your own problems. Or if you're from computer science, then you're sort of developing the next set of tools that will be applicable to a wide range of things. So I really think that, I mean, this is the area that I work in, right? This is what I'm dedicating my research to. So I think it's an area of huge potential. I think it's an area where we really can change the world and address this large problem facing society here. And I hope that you will go on and continue to do such things in the future. All right, so I should say that we're signing off for the people watching on video, if there's anyone that got this far in the actual video.